We're going to cover tests of independence today as a follow-up on the test that we can run with the chi-square distribution. Just a quick programming note, there are other tests we can run with the chi-square distribution, just like there are other tests we can run with the F distribution, the Z and the T distribution. These are just some of the tests that we are covering that highlight a lot of the different things done in statistics. A lot of the things that we aren't covering are either more computationally intense, or they're more specific cases that come up less often, things like that. So we're going to see a second thing that we can do here with the chi-square distribution in this video. There are others though. First, we have to define a contingency table. Why is that? As I mentioned in the previous video, a goodness of fit test is a test where we have one variable and we see, is that variable distributed in a certain way? Again, key point, make sure you remember that, make sure you know that statement right there. A test of independence, however, is a two variable test. And we are testing, again, the counts of two qualitative variables, just like we were before, but now that there's a second one we're testing, is one of them independent from the other? So since we have two variables, we have to figure out how we're going to look at this data. You can't just list all the points. And we do that by what we call a contingency table. So you don't need to memorize what a contingency table is as much as it's a phrase that I'm going to use as referencing what we're doing. So you just need to understand a contingency table and with regard to being able to understand what's happening. But it's not a definition that I'm going to ask for in an exam or anything. It's also called a two-way table, and it's basically just a table with rows and columns, where each, one of the row outlines one variable and the column outlines the other variable, and then each cell is going to have a different count for each of the possible intersections. And so the idea of a contingency table would be that on the one axis, you might put someone's hair color, and on the other axis, you might put their eye color. And so you would list out for hair color, blonde, black, brown, red, other. For eye color, hazel, blue, brown, other. And that creates, a little 5x4 whatever table. And then that makes 20 individual cells, where each cell then has the count for each person who meets both qualifications. And so then you have row totals and column totals. The column totals or row totals, depending on which way you aligned it, would be how many people have that certain color hair independent of their eye color. And then how many people have that eye color independent of the hair. That'd be what when you add up the columns and the rows would tell you, whereas each individual cell will tell you the number of people who have both that specific hair color and eye color. And a test of independence is just a test to see if the row and column variables are independent. So it's very straightforward. We're trying to see if these two variables are independent. Note that we will do a different type of test of independence later. So a test of independence, you cannot just say, oh, I see the word independent or dependent, that means it's a test of independence. It's key that the variables that we are working with here are the counts of qualitative variables. That is very key because we're going to do some tests of independence in the next set of videos, but the variables will be quantitative, not qualitative. So again, understanding what you're working with, it sounds like a boring detail, but it's very important to picking the right type of problem. Okay, we're seeing if the row and column variables are independent. Again, the row and column variables are counts of qualitative data. Very, very key point that you have to make sure you understand. Some notation here. We still have O to represent the observed count, just like before, but notice we have two subscripts. That's because we have to specify which of the row variables we're referencing and which of the column variables we're representing. Before, we only had one subscript, we only had one variable, so we just had to say which group we're in. But now we have a row variable to worry about and a column variable. The row variable is going to use the I, the column variable is going to use the J, and when we say capital R and capital C, we mean the total counts for that row. We have an expected count just like before, and then lowercase r and lowercase c are going to represent the total number of rows and columns. So the process for running this test is going to look very, very similar as before. The differences are going to lie mainly in the hypotheses. There is only one option for the hypotheses. There's not two as there were in the previous one. So the two variables are independent or not associated or not related. The two versus the two variables are dependent, associated, or related. The degrees of freedom are going to look a little bit different. Our degrees of freedom are going to be found by taking r minus 1 and multiplying that by c minus 1, so key difference there to note. But the test statistic works out the exact same. Other than that, everything else is the same as the previous test. So I don't have you write it down a second time. You've already written down the step 5 and step 6 stuff probably a dozen times by now. It's always the same. In this case, your rejection region is always going to be to the right. Our p-value is always going to be greater than or equal to because we only deal with right-tailed tests working with the chi-squared distribution, so everything should line up pretty similar. And so for an example, is there a relationship between marital status and happiness? We asked almost 3,000 people their level of happiness and marital status. Notice again, I know that I have qualitative data because the individual responses are married, widowed, divorced, separated, never married, very happy, pretty happy, not too happy. These are all qualitative variables. And again, the data that we're analyzing is the counts of said qualitative variables. Very, very key to make sure you understand that. And the question is, does simple evidence suggest that one's happiness depends on one's marital status? So is related to, depends on, is associated with. Again, those would all be synonymous questions. As we did before in these problems, it's a good idea to go ahead and find those expected counts and go ahead and put those before we put it next to or below the data. Here I've left you some room in your notes to put those expected counts in each cell. Okay, and so to find the expected counts, what you need to do is you need to multiply the r times c and divide that by n. That is the row sums and the column sums. And so the idea is for this first block here, I need to know how many total people are married. That's the sum of this column. Add those three numbers up. That'll tell you the total number of married people. That will tell you the sum for that column. And how many people are very happy. That's the sum of that row. It's broken up on the slides. It's not in your notes. Would be those four numbers added up there on that the top row. And that gives you the row sum. So now you have capital R, capital C for this cell. Multiply those, divide by n, get you that expected count. And then it's lather, rinse, repeat. You're going to need to find all of the column sums and all of the row sums. Okay, and then once you've done that, again, multiply the row sum times the column sum, and that for that cell, divide by n, and that gives you the expected count. And you should land at these numbers. Once you have those numbers, it's relatively downhill from there. Notice in our outline, I put the two variables. You can actually go ahead and write out what they are. Right, the two variables are marital status and happiness. The null would be that they are independent. The alternative that they are related. Again, lots of different ways you can write that. Just kind of pick your favorite flavor there. Remember, independent, not associated, not related would be the null. Dependent, associated, or related would be the alternative. Remember, we're always checking our sampling methodology. We're asking ourselves, do we have any form of bias? Could you potentially see a source of response bias here? Would people potentially lie about if they're happy in their marriage? Maybe, maybe not. I think this one's kind of great. You can kind of make the argument either way. Remember, on exams, I'm not trying to trick you. I'm trying to give you situations here just to make you think in the notes. Hopefully, you'll see something on the exam and it'll jump out at you. So in the exam, you won't see anything that's really as gray. But here, I do want you to think. You could come to the conclusion that people would lie about their happiness. But you could also come to the conclusion that they wouldn't, that this is a survey, you're talking to someone on the phone or someone on the street, they don't know you, they don't know your spouse, you could make the argument that people would be more honest than ever to them because this is the one person that there's no ramifications for, right? So you could say, yeah, this totally seems fine. I don't see why people would lie about this. Or you can come back and you could say there might be some response bias because people might lie in this regard. And in this case, I think either answer would be acceptable as long as you have a good justification there. And then we're always checking our mathematical assumptions. In this case, we just have to check our expected counts. All of them are greater than 5. Notice I'm going to make a second table when I find the test statistic. Why is that? Because I'm going to have to find the sum of observed minus expected squared divided by expected. I have all the observed on the top of the page, the top of your notes. You should have all of the observed counts as the small numbers. So in that first upper left-hand column, you have 600. Then we have the expected counts, 435.02. I need to do observed minus expected squared divided by expected. That's a little bit of math, and so I'm going to make a duplicate table, and I'm going to put that value in each one of these cells of the table. So when I do observed minus expected squared divided by expected, these are the values I would get. As we talked about before, be careful, make sure you understand that observed minus expected in parentheses, even if you get a negative number, when you square it, that's going to become positive, so you should not have any negative numbers. And then the chi-square test statistic is the sum of all of those numbers, which I get to be 224. We draw our rejection region. Again, we have a right tail test. Our test statistic is definitely in that rejection region. Our critical value would be 12.59. I got 6 degrees of freedom. How is that? Degrees of freedom for this test is R minus 1 times C minus 1. There are 4 columns. So 4 minus 1 is 3. There are 3 rows. 3 minus 1 is 2. 2 times 3 is 6. And our p-value, you could plug this into Excel. It would be about 0. Just make sure you don't fall prey to the fact that Excel might give you, or your graphing calculator might give you some answer like 4.5 e negative something, right? What that's saying is times 10 to the negative something. That means we're moving the decimal place to the left. So don't write 4.5 because it would be 4.5. And I don't know exactly what this one is. Don't take 4.5 as gospel there, but don't write whatever the number is unless you write the times 10 to the negative whatever that power would be, because that is saying that we have to move the decimal place over. Without that, you're saying the answer is 4.5, which is a silly answer. A p-value is a probability. Probability can't be 4.5. It can be 4.5 times 10 to the negative 8 or whatever. Really, really small number. And so rather than writing that out, anytime I have a situation where it says, hey, move the decimal 6 places or something really large, I just say it's approximately 0 and move forward with life. Because we have a really small p-value, we reject the null. Because we reject the null, we can conclude the alternative. The alternative is that these two variables are related, so we can conclude that marital status and happiness are related. However, keep in mind, we did have a discussion around sound sampling. If you thought the sampling was fine, you move on. If you think that we might have some response bias, this would be a place where you come back and say, however, there's this caveat. Next example, we want to learn whether the amount of prenatal care and the wantedness of pregnancy are associated. So again, related, dependent, associated, all words that we can use in these problems. Now we have a 3x3 contingency table rather than a 4x3. But it's lather, rinse, repeat from here. So again, if you feel bold enough, you can kind of work through and see if you can get the right answers and then follow up with the answers. If not, that's okay. But we're going to do the same thing that we did last time, which is first we're going to start off by finding all the expected counts. We're going to do that by adding up all of the values for each row and each column. So that means we'll have a sum for intended, unintended, and mistimed. We'll have a sum for less than 3 months pregnant, 3 to 5 months pregnant, and more to 5 months pregnant on when the care began. And then we're going to multiply those values together and divide by the overall N, which is 939. You could confirm that 939 by adding up all of the values inside the table to arrive at our expected counts, like so. Same idea with our hypotheses, independent versus dependent, not related versus related, not associated versus associated. And again, I just go ahead and put the what the variables are rather than just the two variables, a little more detail there. Same question as before. Is the sampling methodology sound? In this case, I would say um, you're probably a little bit safer there than you might have been before. People tend to lie more about their happiness than they would lie about when they started getting prenatal care. We also have to check our expected counts. One of them is less than 5, so there is some concern there. As before, I'm going to make a separate table to do those observed minus expected squared divided by expecteds. Sum those up. Our degrees of freedom in this case are going to be 4 because we have 3 row variables and 3 column variables. So 3 minus 1 is 2. 2 times 2 is 4. Give me a slightly smaller rejection region, but our test statistic still falls inside of that, and our p-value we can use Excel to find. Also very small, but not quite 0. And so same idea, we are going to say that we can reject the null and conclude that the 2 variables, amount of prenatal care and the wantedness of pregnancy, are related.